Hello, and welcome to AI for Mechanical Engineering. In today's lecture, I'll be touching some preliminary math topics that are essential to understanding the concepts later on that we will be encountering. In particular, I'll be reviewing some basic concepts from linear algebra. So without further ado, assume we have a set of linear equations where in this example, we have two different equations and two unknowns. Now, if you recall from high school math, in order to solve for the solution of this set of equations, we simply multiply the second equation by 2 to get the following, and add it to the first equation to eliminate x1 and we end up with x2 is equal to 5. Now we substitute this in either equation and we've essentially solved for both unknowns for these equations. Another way to do this is to represent this set of linear equations in vector form. So with our matrices and vectors A, X, and B defined as the following, we can represent this set of linear equations as the following. Here, in order to solve for our solution, we simply have to multiply both sides with the inverse of A, which in turn gives us for our solution. Now, of course, we're assuming that the inverse of A exists and that we can solve for the value of this inverse. Now in this example, we could solve for the inverse of A because we had a 2 by 2 matrix. But if we have an extremely large matrix, sometimes it might be difficult to compute the inverse. Now the good news is that we do not have to compute the matrix inverse ourselves, but instead we'll be using a Python module known as NumPy. To do this, we first have to define our matrices and vectors into a data type that Python can interpret. We'll be using NumPy array to represent our vectors and matrices, and in NumPy array we represent a matrix in terms of its rows separately. So our first row comes here, followed by our second row, and each row is represented with these brackets. Now the same holds true for B, and because it is a column vector and we only have one element per row, B becomes the following. And once we've defined both A and B, we can use NumPy's dot inverse to compute the inverse of A, and to compute the product between a matrix and vector, or a matrix and matrix, we use NumPy's dot function. And in turn, you can see that we solve for the same solution. The second approach is to use a data type that NumPy can directly interpret as a matrix. And we can do this by using NumPy's asMatrix function, simply by feeding our arrays that we've previously defined. And by doing so, we can simply use the multiplication sign to represent the product between vectors or matrices, and use dot I to represent or compute the inverse of a given matrix. And again, you can see that we have the same solution as before. Now, if we extend this example to a case where we have a lot more equations and a lot more unknowns, in this example, we have m different equations and n total unknowns. We can take the same approach and take the coefficients of each unknown and represents it as our A matrix. So with our vectors and matrices defined, we can represent this system of linear equations in vector form, or matrix form. Now I'd like to take a closer look at the two different ways we can view this matrix. And the first way is to view the matrix in terms of its columns. The second way is to write out or view the matrix in terms of its rows. So for the first example, if I write out a matrix, an example matrix, each column can be seen as a column vector, which I'll be denoting as A1 here. This becomes A2, and this becomes A3. And this in turn becomes a collection of independent column vectors. The second way to represent this matrix was to view it in terms of its rows. So this time, if we have the same matrix, and look at each row independently as a transpose vector, in which I'll be denoting as B1 transposed. The same holds true for the second row. A can be seen as a collection of transposed column vectors. So here are two different ways we can represent our matrices. And this is an important concept, so I'll be revisiting this later. But with this in mind, I'll be talking about some operations within the vector space. So although there are different types of products within the vector space, the type of product that I'll be talking about is the inner product. And within a Euclidean space, we can also call this the dot product. So by definition of an inner product, we're multiplying both vectors element-wise and taking the summation over the entire vector. So for instance, if we have two vectors x and y, and if we write out the inner product, simply take the transpose of x and we have our answer. To implement this in Python, we simply have to use NumPy's dot function, which is what we've previously used to represent the product between a matrix and a vector. And to represent a transpose, we simply have to add dot t to the end of an array. Now, because we had a second way to represent our arrays, we can use NumPy as matrix. And in this case, instead of using NumPy's dot function, we can simply use the multiplication sign to represent the products between two vectors. Extending this example to a matrix to vector product case, I'd like you to recall the two different ways or two different views that we can have on matrices. So first of all, if we write A by its rows, the product of A and X becomes an inner product between the rows of A and X. So for instance, if I define A as the following and X as the following, and in order to solve for AX, we simply take the inner product of this row and this column, followed by this row and this column. And because we've previously called this row a transpose column vector, we can represent AX as a collection of inner products between the rows of A and X. And if we extend this to a more generalized case, this becomes the representation of an inner product between A and X if we write A in terms of its rows. The second way to write out our matrix was to represent it by columns. And by doing so, AX becomes a linear combination of the individual columns of A with the weights given by X. So again, if we take the same matrix, for example, this time if we group x1 together and look at which terms are multiplied with this, you'll notice that this is being multiplied with x1, and also this is being multiplied by this one. And because we've called this column vector A1 and the second column vector A2, the inner product of A and X simply becomes A1, our column vector, weighted by x1, A2 by x2. And again, if we extend this example to a more generalized case, AX becomes a linear combination of the column vectors weighted with coefficients given by X. So based on the two different ways that we could represent our matrices, the inner product of a matrix and vector can be seen in two different ways. Now, before I move on, I'd like to mention an important property of matrices in terms of symmetry. So by definition of a symmetric matrix, the shape of that matrix must be square, and the transpose of itself must be equal to itself. So for instance, if I define A as the following, for A to be symmetric, if I write out the transpose, you can see that regardless of the diagonal elements, these have to be identical, implying that B is equal to C. Now the key takeaway here is that symmetry is defined with respect to the diagonal axis instead of any other axis. And another interesting property of symmetric matrices is that for any given matrix, if we take the transpose of that matrix and take the product with itself, we always end up with a symmetric matrix. So to show this, if I denote this as B, we simply have to show that B is equal to B transposed. And if I write this out, we get the following. And as you can see, we were able to show that the transpose of B is identical to itself. Now I'd like to talk about something called norms. So norms can be seen as a measure of strength or distance within a linear space. And I personally like to view this as a measure of size. By definition, a norm is any function that satisfies these properties. And because a norm can be seen as a size or a strength, it is always greater than or equal to 0. And if the norm is equal to 0, then the vector itself is also 0. The second property is that if we scale a vector with a constant and take the norm of that, we get the same result as scaling the norm itself with that constant. The third property is that if we add two vectors and compute the norm, we will always have a value that is less than or equal to the two norms added separately. And because I said that the norm can be any function, there exists more than one definition of a norm. And the first type of norm that I'll be introducing is the L2 norm. And I'm pretty sure this is the type of norm that most of us are most familiar with. So within a Euclidean space, the norm can be simply seen as the distance from the origin to a vector. So this corresponds to the L2 norm. And another way to view this distance is to individually add up each component separately. So this corresponds to the L1 norm. And for a more generalized case, we can have something called a p-norm, which is defined as the following. So this implies that there technically can be an infinite number of different norms. And from a notation standpoint, we use two vertical lines on the left and right of the vector to represent the norm. and on the bottom right indicates the type of norm that is being evaluated. So for instance, this becomes the p-norm of x. For the implementation in Python, we can simply use NumPy's function np.linearalgebra.norm to represent or to compute the norm of x, and the number here represents the type of norm that is being evaluated. So for instance, if we have a vector x, the 2 norm, or the L2 norm, can be computed as the following, and you'll notice that we have the same answer. The same holds true for the L1 norm. And again, we get the same answer. So now that we've talked about the size of these vectors, I'd like to talk about angles. Before I talk about a more generalized case, I'd like to talk about a particular case where two vectors are orthogonal. And if you look at the definition of orthogonal up in the dictionary, you'll find something that involves a right angle. Now, the mathematical definition of orthogonality of two vectors can be defined as the following, where the inner product of these two vectors are equal to 0. I will be talking about why this is the case briefly. However, for now, just keep in mind that if the inner product of two vectors is equal to 0, then those two vectors are orthogonal. And then we have another special case where two vectors are orthonormal. Now, by definition, two vectors are orthonormal if they are orthogonal and the norm of each vector is equal to 1. This is another specific case where the vectors are both orthogonal and have a norm equal to 1. Then what about a general case? The angle between two vectors can be expressed as the following. Now, before I talk more about this, I'd like to quickly review a geometric view of inner products. Suppose we have two vectors, y and x. If we take the inner product between x and y, we're simply multiplying this length with this length. And if we look at the first component here, you'll notice that corresponds to the norm of x multiplied with cosine theta, and then multiplied with the norm of y again. And if you group these terms together, and reorganize this equation, we get the inner product of x and y over the norms of x and y. And to solve for the angle, we simply have to compute the inverse cosine of this term. So this gives us the general expression for an angle between two different vectors. Now, if we revisit the definition of orthogonality, you'll remember that this term was equal to 0, or the inner product was equal to 0. And if we take a closer look here, you'll notice that the norm is always greater than or equal to 0. So as long as x and y are both non-zero, the inner product will be equal to 0 if cosine theta is 0. If we quickly draw what a cosine plot looks like, this is cosine theta. You can see that cosine theta is 0 at 90 degrees, which corresponds to the orthogonal case. Now, based on this formulation, we can define something called a half space. Now, the half space can be seen as a collection of all vectors x that satisfy this relationship, and this concept comes in important later on when we learn classification algorithms. So based on the expression that we've used in the previous slide, the inner product can be expressed as the two norms multiplied with each other, multiplied with cosine theta. And for this entire term to be less than or equal to 0, because the norms are always greater than or equal to 0, this term has to be negative. So assume we have an arbitrary vector y, and let's redraw the plot for the cosine. Now the region where cosine theta is equal to 0 corresponds to this region, which is where theta is in between 90 degrees and 270 degrees. So this implies that the angle between y and x is at least 90 degrees up until 270 degrees, which in turn defines this entire half space with an outward vector y and a boundary passing through 0. Again, I won't be diving too much into the details here, but I'd like you to keep in mind that half spaces can be conceptually used in classification algorithms. In today's lecture, I've briefly reviewed some basic concepts of linear algebra regarding how we can formulate systems of linear equations into matrices, the different types of views that we can have on matrices, some special properties, and operations, and so on. This is the end of today's lecture, and thank you.